Hello, everyone, and welcome to our webinar today, How to Build a ChatGPT app using JSON data and single store Chi. My name is Matt Brown, and I'll be your moderator today. Before we begin, just a few logistical reminders. Today's discussion is being recorded, and you are currently in a listen-only mode. You may submit questions throughout the session using the Q&A functionality in the lower section of your Zoom console. If this is your first time joining a single store webinar, heads up that we present weekly technical workshops demoing data and AI use cases and new technologies. In fact, next week, we will be presenting how to drive 100x faster analytics for your MongoDB apps. During that time, Senior Technical Evangelist Akmal Chowdhury will show you how to drive 100x faster analytical queries on JSON using a MongoDB API that doesn't require any query changes or data transformations. It's very cool. If that topic sounds fun to you, feel free to register right now at the link that's on your screen or that QR code that you see on your slide. I will also paste this link into the chat in just a moment. But let's get back to today's topic. FYI, we have fantastic technical experts who will be joining our Zoom Q&A. They have a good grasp of the technologies involved. They're ready to answer your questions as they come in. So please welcome Akmal, Vijay, and Eric Hansen. We'll try to get to as many of your questions as we can as they come in interactively. I will also try to note a few for our live Q&A at the end of today's session. We'd love for you to try out today's technology. In fact, anyone who tries it out today will be entered for a chance to win new branded AirPods Pro. All you need to do is click this link that's on your screen, that bit.ly link, or hit that QR code that's on your screen, log into Single Store, either a free trial if you're a brand new user, existing account if you're already a customer, ongoing trial. Either way, we will check the folks who have logged into this link, and then we'll announce a winner by the end of today's session. So let me introduce our speaker for today. Jason Thorsness is a Senior Director of Engineering at Single Store. He's spent over 16 years at Microsoft, where he rose through the ranks and became a principal software engineer. Most recently, he's been hard at work here, laboring to bring the power of Single Store's vector search and fast analytics to the MongoDB API ecosystem. Welcome, Jason. You now have the floor.
Thanks, Matt. Okay. I don't know about laboring. It makes it sound less fun, but this is all pretty fun. And I have been working on JSON and the stuff that you're going to see today. So what will you see today? I'm going to go over how to generate text embeddings from JSON data using OpenAI APIs. How to store the JSON and along with the embeddings efficiently in single store Chi and single store DB. How to query those embeddings with vector semantic search, which is really cool. You'll see that in a bit. And then finally, how to teach ChatGPT to build the queries for you using the embeddings and other fields in the JSON data, which is really, really cool. So we'll get to all this in a bit. And Single Store DB as a platform provides a unique combination of features that really make this scenario work well. So let's talk a little bit about Single Store DB for those of you who might not know much about it. Single Store DB has a kind of a core storage engine that combines row storage concepts with column store. We call that universal storage. And that kind of core storage engine provides a platform for a lot of different scenarios. It can do real-time analytics across large amounts of data by relying on some of the column store ability to aggregate quickly. But it can also do ultra-fast like point lookups using some of the row store capabilities. So it really the one engine can support, I guess you'd say, multiple types of use cases. It also has a fast ingestion and CDC pipeline to bring data in from other sources, and it runs in any of the major clouds or in your on-premises data center. Additionally, single store supports a wide variety of data types so that you can store the sort of data that you have. We have traditional relational data. You can have geospatial. There's classic full text search, key value features, JSON data, which we'll be using, and also time series and vector operations, among others. And by virtue of supporting all these different data types, you're able to keep it all in one engine and not do kind of more complicated multi-data store operations from your application. And today we're really going to be focusing on two of those data types that I mentioned, JSON and the vector functions for semantic search. The nice thing about having it in one database is we can use these together in a deeply integrated way, which I'll get into. Before we jump to I will talk about the demo first, and then I'll give a bit of background about some of these concepts. Okay, so the demo that I put together today uses a bunch of data from something called the Open Library. The Open Library is, 1 second. Just want to make sure that I never got a signal that my audio is working. Yes, okay, sorry about that. Okay, and back. Didn't want to give the whole presentation with my microphone not activated. Okay, so let's go back to the demo architecture. So I took this data set from Open Library. Open Library is a project of the Internet Archive, and that is it's kind of like a universal library where anyone can go check out book information, check out books, and find books that they're interested in, like any other library, except it's open to anyone. They dump a data set of all of their data, which you can use for finding projects like this one, where we're going to search over the book metadata as an example of text embeddings. I took about 340,000 records. This represents all the fiction and nonfiction books in their database, and brought that into a loader program that's written in Node.js. Node.js loader program uses the OpenAI SDKs to generate embeddings for the information in the book data, like titles, descriptions. All of that is fed into the OpenAI APIs to generate the embeddings. And then the program uses the MongoDB client to load all of that data into single store through single store Kai. Then we flip over to the other side, where we have a client application. This application is written in Next.js 13. It's a simple example of a search application. It will use OpenAI APIs to generate embeddings for a search query provided by the user, and then submit that to the database to find matching items. And then we'll show the next step of that, which is to use the ChatGPT APIs to also add structured query over the JSON fields. But before we jump into the code behind this, let's go over a few of the concepts. So kind of fundamentally, what is an embedding? So like concretely, it's just a list of floating point numbers that represents a normalized multidimensional vector. So you might think of a two-dimensional vector as like an arrow drawn on a chart, where you can calculate the similarity between vectors through operations like dot product. For these multidimensional vectors, they might have like 1,000 dimensions, but you can still use that same dot product function to calculate how similar they are. And the interesting modern piece of this is the embeddings are generated with these large language models, and they're the model's representation of the meaning of some input text. And the model is trained on a whole bunch of data from the internet and other sources. And these, like its representation of meaning is pretty close to how a human would think about it. So when you calculate the similarity between embeddings using the dot product operation, it tracks very closely how a human would think of the similarity between the text. And I'll show some examples of that in a bit. It's much more powerful than classic full text search that's looking at just the words in the text. So how can text embeddings be used in single store DB? So single store DB has a mature set of SIMD accelerated vector operations. We've had this for a number of years, and recently it's becoming very popular. All you have to do is add a blob column to your table, store the embeddings there, and then you can use functions like dot product and other associated functions to calculate the distance between the stored embedding and an embedding in your query in order to find the closest match. This can be extremely fast, and it can be combined with other conditions in your query and other database features without requiring any kind of special client or extra queries to other sources. And finally, let me say a bit about how JSON works in single store. So JSON is a super popular data format for the web. It's a structured combination of nested objects and arrays. When you insert JSON data into single store understands its structure and uses a specialized columnar format to provide really efficient compression and query performance. So it will look at kind of the schema of the JSON and then store it appropriately for that structure, not just as a text blob. Single store Kai provides a MongoDB compatible interface to work with JSON data and other data in single store. And so that means that applications that are written to use MongoDB can use single store and take advantage of single store's JSON acceleration features. And we've observed analytics queries in particular can be highly accelerated, often 100 times faster. And also, any MongoDB application can leverage single store's other advanced features like these vector search operations that I'll be demonstrating. So yes, finally, let's move to the code. Okay, let me adjust these slides here. Before we jump to the code, to follow along with this, and if we haven't shared the GitHub link, we'll share the GitHub link at the end of this presentation. You're going to need a single store endpoint. It's simple to get one. Just go singlestore.com/Kai, and you can click try single store Kai here, and you're brought to this trial page. You can sign up. You get $600 of free credits. It's like 4 clicks. And this will provide you with what you need to reproduce the demonstration that I'm about to show on your own. Okay, so let's talk a little bit about the code. And I am pulling my editor over here. Okay, hopefully everyone can see this. I have this single store Kai examples GitHub project, and the example that we're talking about today is this ChatGPT example. This is a combination of a loader program to load the data and a Next.js program to consume the data. Here's an example of what this data looks like. This is book information from the open library. So we have somewhere here the title of the book, the subtitle, a set of subjects in an array. There's different timestamps, relationship to covers, some stars information The stars information, keep in mind, I added that as synthetic stars. I didn't use the actual reviews from Open Library. So when you see a book that you think is really great, rated 1 star, it's because it's just random. An author relationship, etc. So this is sort of some typical lightly structured JSON. The data set from Open Library, I grabbed all of the fiction and nonfiction works, and that came to about 340,000 items. The next step was to get embeddings for those items, which uses this prepare works script. So this is a fairly simple Node.js program. It uses your OpenAI key to for every line of the input file, which is going to be representing it's one piece of JSON per line. It takes some fields from that, which we want to generate the embedding for, here the title and the description, and then it submits those in a big batch to OpenAI. It's like 20,000 like length. The buffer can be 20,000 characters long at a time, and that's because OpenAI has some content limits per call. But the more you can put into one call, the faster things go. It's better to do fewer batched calls. So this goes through every line and generates the embeddings, and then stores the original document along with the embedding into an output file. After that, we use a loader program that will use the single store Chi endpoint, which you can get from that trial page, to basically just load all of those JSON documents into the database. In this case, it creates the collection. When it creates the collection, it uses a single store extension, which is to specify that the collection, in addition to the JSON data, has some structured columns, and we want to put the embedding into a long blob column. And the reason for that is the single store operations that work over vectors work most efficiently over these long blob columns, so it gives us some better performance. So this is just a and then I also added some stars to the document and pulled out the first author to make my query easier later. It pushes in batches of 1,000, and this loads very, very quickly, much faster than generating the embeddings in the first place. So this is the extent of the loader program. The generation of the embeddings and the loading is less than 100 lines, I think, each. So it's not a whole lot of work that you have to do to get the data into the system, and then we can start querying it. So let me talk a bit about the application that we will use to query this data. So it's a Next.js 13 app. It's got 3 simple pages. The first one will just demonstrate getting the embeddings. So let me start this app up. So I'm just going to run the development server locally here. And now we should be able to refresh this. And it will compile this page again, and there we are. Okay, so let's look at first getting some of these embeddings that we're going to use for our query. So that page will do the following. It takes as an input 2 text strings. It will call OpenAI to create the embedding. It's important we're using the same model that we used for all the book embeddings, for the query embeddings. You have to use exactly the same model. And then in order to calculate the score, I'm just executing this SQL query that takes the dot product of the first embedding versus the second and outputs the score. And this uses a single store chi extension where I can use any arbitrary SQL to query my my data in addition to all of the MongoDB operations. And I did this just for simplicity here, since I could do it in a one-liner. So let's see an example of that. So we'll go to the first example. And let's talk a bit about these embeddings. So let's take, for example, apple pie as one text string and apple M1 as another text string. When I click submit, this is going to go to OpenAI, generate the embedding, then go to single store and get their score. And in this case, it says these are pretty close, right? They both have apple. The model says, based on the embeddings generated by the model, their score is 0.84. The scores are arranged from 0 to 1, and this is a pretty good score. However, what if I replaced apple M1 with blackberry pie? Blackberry cobbler. So in this case, we don't have any words the same. It's not related to apples. But when I submit this, I will get a higher score. And the reason is the meaning represented by these, according to the model, is closer between apple pie and blackberry cobbler versus apple pie and apple M1, because it sort of understands, for some use of that word, that apple pie is a food versus apple M1. So this also can incorporate like seemingly knowledge from the world. Like, let's take another one here. A ship hits an iceberg and sinks, and combine that with the word gigantic. These don't seem very similar, and in fact, it's a pretty low score. However, if I replace gigantic with sort of a synonym, Titanic, at this point, the score is really high, and that's because the model has embedded similar meaning into both the word Titanic and the ship that hits an iceberg and sinks. And this sort of meaning-based comparison leads to much more relevant search queries in many situations. I have one more example here that will bring us sort of closer to the book search, which we'll look at next. How about, why did the software developer cross the road? And let's compare that to a possible book title here, which is A Programmer's Guide to High Performance Databases, such as Single Store. And we'll click submit. And this is not too close, 0.76. However, if we change it to A Programmer's Guide to High Performance Jokes, now we have a higher score. And it's this kind of nuance that the model, teased out, that the first one is probably related to a joke because it's that standard joke format that can get you just the, slightly better search results that can power better applications. And if anyone is wondering, it's to get to the other side. Okay. So that's it for generating the embeddings. But now let's use those embeddings to query the database. So I'm going to jump back to the code here. Let me pull this back over. So for querying the database, we're going to take a query from the user, generate an embedding, and then use it to find matching results. So that's very similar to what we just saw. We take the OpenAI key and we generate the embedding using the same model from the user's input. And then after we have that embedding, we get a Mongo client, which will be used to query single store chi. And we generate just a regular Mongo aggregation query. So here we use add fields with a single store extension operation called dot product to take the embedding, to take the dot product of the embedding versus our stored embedding. We make sure that the score is at least 0.78, which is just kind of a relevance threshold that suits my data set. And then I project out a bunch of the JSON information sort the data by the relevance. Z here is the calculated score of the embedding. Do a lookup into another table of author information that I had also loaded, and a final projection. This is all just standard MongoDB API stuff that you do. Then I render it into a page of results. So let's take a quick look at how that plays out. Second. Okay. And before I search this, I want to talk a bit about the alternative. So let's go to the actual Open Library. This is the Open Library website. The Open Library is great. And it has a pretty good search experience that I believe is based on more traditional full text search. If I enter a search query here, hobbits throw ring into Mount Doom. I know that this is one of the Lord of the Rings book. I don't know which one. I just type what I think happens and I get no results. I think that the computer system behind this should know enough in order to get me some results for this query. Let's try the same thing in single store with semantic search. So hobbits throw ring into Mount Doom. And there we have the Fellowship of the Ring as the top result. I think that's actually, okay, I think, yeah, Return of the King is the one where they actually throw it, but it's sort of what I was looking for. And so you can see that by looking at the meaning behind the text rather than the actual words using these semantic search features, it can be a more relevant search experience. Now, here's a problem though with semantic search. Say I was not actually looking for the book. I was looking for some information maybe about the book or about J.R.R. Tolkien. I can add here nonfiction to this. And it's done querying. It didn't change. It didn't help me because the semantic search is always a little bit fuzzy. It doesn't understand or it can't express in the embedding vector the fact that nonfiction and fiction are really very distinct sets and shouldn't overlap, and that I was requesting nonfiction. So how do we get more relevant search that can actually understand that kind of concept? So one thing that I could do is I could build a structured query builder here where there's some selectors on the left, and I can pick nonfiction. I can maybe from drop downs, that sort of thing. And I am not, UI development is not my specialty. I used the power of ChatGPT to help me do the UI that you're looking at here. And I don't want to tackle that. And that's an expensive proposition to create a structured query builder. And it's also harder for the user to use. I want to just write this. So how might I do this using some of the new AI features? So that's what we can get into now. And that's using the ChatGPT APIs. So let me get back to the code for this segment. So this is going to do something again, very similar, but slightly less. And you saw a preview there of what's coming up next. Okay, so in this one, we're using a feature called Type Chat. Type Chat is a library published by Microsoft that helps you craft structured queries to the ChatGPT APIs. I think that this is going to be, it was just released like a month ago. It's going to be incorporated into more and more of the standard tools that developers use to query these models. What you do for Type Chat is you define a schema and you put a bunch of comments in it. Like I put a comment, this is a schema for querying the books database. And anything general about the book description or title should go here. And the comments matter because this schema is compiled and then fed to the ChatGPT API for it to understand by the Type Chat library. So I can say that I have a subjects field and it should be, one of these strings, and I explain some of these fields a bit more, tell it to normalize. And then finally, in addition to book and subjects, I have a stars condition here where I want it to provide an op, which is one of the standard MongoDB query operations, comparisons, and a value of 1 to 5. So TypeChat will ask ChatGPT to produce a response that matches this schema, and it will ensure that the response matches the schema. If it doesn't match, TypeChat will tell ChatGPT, hey, you got it a little bit wrong, can you fix it? And it'll go back and forth. Usually it doesn't have to go back and forth, but what it means is that as a developer using this library, I can trust that I'm going to get back a response that matches this TypeScript schema. So what this code will do is it will compile the schema, get the OpenAI AI kind of client set up, and then it's going to take the user's input. It will use TypeChat to get the structured response. And then for each piece in the response, it will optionally add that to the MongoDB query that we're going to use for single store Chi. So if there's a condition on subjects, it will do a match on subjects that it's in the set. If it's a condition on stars, it will add the condition on stars. If we have a condition on book, that's what we wanted to use our embedding for. So it'll go and get the embedding, and then it will add the dot product and then the condition on the score. And then finally, add the rest of the stuff from the pipeline, which is what I had from the previous one, look up the author and that sort of thing. So let's see how this works. Okay, so I'm going to enter the same query that I had before. And it has to compile there. Okay, so with just this, it picks out that this is the description, and I get the same set of results. And now let's try when I really don't want the actual books, I want something nonfiction. At this point, TypeChat is able to ask ChatGPT for that structured response. It identifies the subject that I'm looking for. And instead of returning the fiction books, I get back all these nonfiction books about like the Cliff's Notes, I guess, which is maybe what I'm looking for. So you could do this with the stars condition as well. And I am going to enter another query here. New York Times bestseller, at least 4 stars, Viv the Orc. This is something that I heard about from my friend, maybe. And TypeChat will use ChatGPT to pull out the structure. And it says, okay, New York Times bestseller, Viv the Orc, stars condition, greater than or equal to 4. It's so cool how ChatGPT could do that. And then I get back this book that I'm looking for, Legends and Lattes. So this can be a really powerful search experience. I added only a few conditions here, but you can actually give TypeChat your entire JSON schema and just say, ask ChatGPT to generate like Mongo queries using that schema. If you're willing to trust your user to not do some kind of query that's going to be too hard on your database, depending on the context. But that can provide like really excellent flexibility in querying a JSON data set and combining it with other advanced features like the dot product and semantic search. So there's one more thing that I wanted to show from this. Let's take the same query. And you might wonder, why can't you just use ChatGPT and forget about all this other stuff? Forget about generating the embeddings, forget about the database and all that. Well, let's try ChatGPT here. I'm going to use GPT-4, the fanciest model that they have, and I love this GPT-4. I used it to help me develop that UI, like I mentioned. And let's see what it says for New York Times bestseller, at least 4 stars, Viv the Orc. And as we're going to get this response that we've all seen over and over, as of my training data in September 2021, and the reason for this is this book won like a bunch of awards, but came out in 2022. So it has zero knowledge of this book. Despite that, it was able to, help with querying our database that does include the information on this book. And in fact, the database through ingestion mechanisms can be kept up to the millisecond, up to date with new information. The other thing that ChatGPT can't do is use your internal company information. Like I used the books example here because it's kind of cool. Like I get the book covers, everyone knows the book names that we're searching for and that sort of thing. But you could imagine using your own internal company data. Maybe it's like order records or insurance quotes or some domain specific giant data set that you have. And you're not going to feed the whole thing to ChatGPT. You can't feed the whole thing to ChatGPT, but you can generate embeddings from that data set, store it in a single store database, and then query it using the help of ChatGPT to form the queries or other ways of getting the embeddings as well. So that is why, in addition, that's why having the data in your own database and using some of these features kind of goes well beyond just querying the OpenAI APIs by themselves. Okay, so I think, let me go back to the slides here. I'll say one more thing. All the code that I showed, and I think you'll get a link to this too, it's up on GitHub in Single Store Labs, Single Store Chi examples. The one for the webinar is in ChatGPT. If you have any issue running this example yourself, please let me know. And you could just file an issue here or get in touch with us through the other, feedback mechanisms we'll share. But this should let you generate, get the data yourself, generate the embeddings, load it, and try out everything that you saw today using your own single store instance. Now back to the slides. Okay, and I'll mention again, if you're going to set up your own single store instance, you should use this link. This link will enter you into a chance to get the AirPods Pro. I unfortunately am not eligible, despite wanting to get an AirPods Pro with the single store logo. Maybe I'll get one eventually. But please follow this. It takes, like I said, it's like 4 clicks. For a different demo, I had to do it like 100 times, and it doesn't take very long. Let's see. And this slide, I guess I already sort of talked to. For ChatGPT, it can't get the most recent data and private data. One more thing to mention, why not just a vector database to do these vectors? And I think we saw that as well. It was really the combination of the vector storage with the JSON query capabilities that made this a powerful demo. The one we did in the middle, where it was just querying the vectors, it couldn't do things like the nonfiction piece or the conditions on stars. It was too fuzzy for that. And that's why having a database that combines like other types of structured queries with the vectors is very useful. So I'm going to turn it back over to Matt to close this out. Thanks to everyone for following along.
Awesome. Thank you, Jason. This was an awesome presentation and demo. We can now jump into the Q&A session. Just as a reminder for everyone, that Q&A functionality is at the bottom portion of your Zoom console. Feel free to use it throughout here. We've had a lot of great questions come in while Jason was presenting, so I'll start with those, but we'll also keep an eye on the new questions coming in, so keep them coming. The first question I have is from Anurag. It is, how would you upload the data for around 25 million records with more than 200 250 columns? And is the data frequently updating?
Assuming this is JSON data, or really any data, when it's stored in single store, it's going to be optimized in that column storage format, and 250 columns is not an issue. There could be 250 key paths in a single JSON blob or 250 structured columns, and that's kind of normal, I think. And that type of the amount of data there as well is not really unusual. I think that the how you would upload it. Single store has a feature called pipelines that can do that sort of data ingestion very, very quickly. I usually do it with the single store Kai bulk insert APIs, the regular MongoDB bulk insert APIs, or I use if I'm taking it from a MongoDB database, I use MongoDB dump and MongoDB restore. And for the bulk ingestion, we've really optimized that pipeline, so it goes very quickly. And then as far as keeping it up to date, the way that single store's universal storage works is it will, as data is ingested, it ingests very quickly, and it goes into a row storage segment that is able to allow the kind of very quick updates, very low latency writes. And then over time, when that segment gets to a certain size or at a certain time has passed, it will analyze chunks of that and store that in the efficient column storage format to support better analytics queries. And so what this means for large data sets is you can be continuously ingesting 20,000 rows a second or something, in addition to having a lot of data already, and then run queries that give you up to the millisecond results. And I think I mentioned 20,000 because I have a video that I did of this somewhere up on our single store YouTube, where I show a demo of loading that sort of data. That's something that that's a common need, and so that's a scenario we focused on.
Awesome. Here's another, it's follow-up from Anurag. It's how would we deal with images if we wanted to store and call by query?
So you can generate embeddings from images as well, and that can be really cool. I don't have a demo prepared for that, and the images you saw today were just the covers of the books that weren't actually searched. But you can use a model to generate the embeddings from the images, and then you can use another model to generate compatible embeddings from text queries that then allow you to search those images using the same sort of text querying that I showed today. And those embeddings can be stored and searched in single store in exactly the same way as text-based embeddings. It doesn't really matter how the embeddings are generated. Once you have them in that form and can run the dot product on them, you can do this sort of search on top of them.
Awesome. Here's one from Fat Tran. How about using cosine to compute similarity? What are the pros and cons of this versus the dot product approach?
So from my understanding, dot product with normalized vectors is equivalent to cosine similarity. We also support other operations that are slightly different, like Euclidean distance. But I'm not an expert on the nuance between these different modes, although all the important ones that people seem to want to use are primitives in the single store vector operation set of operations.
Good stuff. Here is another one, a follow-up, same audience member. And by the way, Akmal can also chime in on any of these. I know he's furiously trying to answer these in progress. But the question is Is there a migration runbook for data from other database technologies, such as Postgres, Bigtable, Dynamo, to single store?
Jason, maybe I can chime in, and then if you have some comments. Matt, so of course, we work with lots of customers who do exactly that kind of thing. I think there is no single tool that we have that would assist in that scenario. Sometimes it's custom code that we build. Sometimes it can be done other ways, pipelines, for example, or simple dumps, as Jason was mentioning. I mean, there are different ways that we would do it. And it's a question of really understanding the customer requirements, how much of that data needs to come across, or if it's a complete migration, that might be a lengthy process. We are MySQL Wire compatible, so that's really helpful. And of course, the pipelines capability we have is an awesome way to kind of stream data in from an external source. And that could be, one suitable way to do that. But I think it really depends on customer needs.
Good stuff.
There's a great question there from Catherine, which is kind of outstanding there, Matt, if you say it there. So she's asking, how long does the W get? And this is, I think, for you, Jason, the openlibrary.org dump work latest txt.gz command usually take. So I guess that's for you, Jason. So yeah, how long does it usually take you?
I'm so excited that that means that someone is actually trying the demo. So please, if you have any hiccup with it, let us know. They throttle their download speed. It's annoying. I had to wait, I don't know, like 45 minutes on my connection for it. It's not your connection, it's them throttling their download, I think, to protect their infrastructure. But it won't be too bad. It's like, I think that one is, I don't know, it's under 100 gigabytes. So just go have some patience. That's what I had to do. I walked away and got some lunch or something and came back and it was done.
Interestingly, Catherine's just posted a follow-up there. She says it took around 5 to 10 minutes, which is great.
Oh, well, that's not bad.
Awesome.
Good stuff. Here's another question. This one is anonymous, but if someone uses the input box to try to search the database 1 million times, will the model execute it, or is the model smart enough to stop that search?
So I didn't put, so if you're looking at the code that I put to GitHub, there's no kind of protections against that as is. And if you were to productize this and throw this into your actual application, there's probably a couple things you'd want to do. Number one is if you have, like, often you'll have people use the same query over and over. And so you'd want to have some kind of a cache of embeddings for like identical text, because that'll just save calls to OpenAI. And also you might want to have some type of throttling or just detection of like weird situations like that. If the rate gets too high, if you're generating too many calls to OpenAI, maybe that's something you'd want to rate limit on that particular user. I think what you'd want to do depends on whether this is like an internal application, or if this is something like you could imagine Open Library putting this as an extension to their own search on their website. They might have to be a bit more protective over potential abuse like that than you would for an internal application. But certainly none of the code that I put on GitHub does any of that quite yet.
Good stuff. Another question. This one was from Vinay Kumar. How does the nested data in JSON stored in single store DB, as said, converts into columnar format?
So this is super cool. I've done a bunch of work on this. It uses techniques that are similar to what you'd find in it's not using Parquet, but it's similar techniques to flattening that you might find in Parquet format. So you can go and take a look at how Parquet works. But basically it will, like if you have an array of say the subjects array in the books, it's an array of words. it will create a single column from that array, and there'll just be many, many entries in the column per document. So if a document has 10 items in its array, you'd have 10 entries in that column, and all of those entries would map back to that same document. What this lets you do is it enables compression over like all of the documents and all of the arrays in the document, and it enables extremely fast searching over all of the arrays in all of the documents. This encoding works particularly well for like how array-based searches work with MongoDB query language, where you just do like, A.B, and if B is an array, it'll search in the array. That maps very well into like a single search in a single column in the format that we use.
All right, great. Here's two from Tim Roberts. The first is ADA 002 text model versus GPT 3.5 Turbo or GPT-4. Would we have very different results?
So the ADA 002 text model is a model designed for creating embeddings. It produces as its output like one of these vectors that you can store in your database. It always just produces the vector as its output. So the purpose of that model is for generating the embeddings. And it's also not expensive. And they keep lowering the price. Like it seems like every couple of months they take the price down by a factor of 4 again. So very inexpensive model to use, and you can use it to generate just bulk embedding data. The two chat models, GPT 3.5 Turbo and GPT-4, they are for a different purpose. They can't generate embeddings. They generate kind of whatever you ask for in like free text. And then it's the type chat library on top of that that kind of forces that response back into a JSON blob you can consume. I haven't tried, for the purposes of this demo, the ChatGPT 3.5 Turbo was good enough, like completely good enough to do what it needed to do to extract those pieces from my query and form a structured query. I haven't tried GPT-4 API for that purpose. I know that when I'm asking like free-form questions about like how to write the UI for the demo, and I'm using ChatGPT, GPT-4 is way better at that. So I think depending on the complexity of your query that you needed to generate, you might get better results with GPT-4, but that's not something I had tried for this demo.
Good stuff. A follow-up question from Tim. What about the tokens used? Do you have any idea for your demo?
Yeah, so in the GitHub code, there's like two data sets that I mentioned in the README. One is if you're just looking at science fiction and fantasy books, it's about 30,000 records. And then one is all of the fiction and nonfiction books. And I think the biggest one cost me about I think it was between $1 and $2 to generate the embeddings for all of those items. The smaller one was like, just a few cents to generate those embeddings. So it's not too expensive. I think that there's other ways to generate embeddings too. You don't have to use the OpenAI APIs. And in fact, you can still use their ChatGPT APIs to generate the structured queries, even if you use something else to generate the embeddings. And so if you have your own models hosted or some other service, you can also generate bulk embeddings with those too. But if you're just looking to reproduce the demo, it's a couple dollars at most with how it was working for me.
Good stuff. Here is another question from Fat Tran. I know this question has actually come up in previous recent webinars. So, Akmal, you can chime in too if you want, or, I'll pose it to Jason. But the question is, What are the advantages and disadvantages of single store over other popular competitors like Pinecone, pgvector, DuckDB, etc.?
I can offer my perspective on that, and then maybe others can chime in. But the big one for me, I've used Pinecone a little bit just to try it. I followed some examples, and it's very focused on the vectors and storing different vectors, and you can add metadata to them, but the ability to do structured queries over that metadata and to have other sorts of operations like geospatial and such falls a lot. It falls way short compared to a more general purpose database like single store. And I really think it's the combination of the vectors with other more traditional database capabilities where you get the most value out of even using vectors in the first place. I think single store compared to Postgres and pgvector has there's a lot of differences between those databases, especially in their performance characteristics. I don't know if someone else wants to chime in on some of that,
yeah, Jason, this is Vijay. Let me chime in a little bit on that. So compared to, if you say comparing single store against a core specialized vector database, right, like a Pinecone, Milvus, VV8, or Zills, I would say there are a few key differences. Number one, most of them don't support SQL, right? So you have to use custom code or custom programming languages, which gives you really not much of a flexibility or analytical capabilities, right? So that's number one. We are relational, but again, as you saw today, we also support JSON, vectors, time series, a bunch of other data sources, right? What that means is if you use something like Pinecone, it only supports vectors. You don't have an ability to combine that vector data with other types of data types, right? More importantly, one key thing which I think Jason referred to today was the concept of a hybrid search, right? So how do you do a semantic search with a full text search in a single SQL query, right? Things like that, which is really not possible in a very vector specific database. Again, keep in mind, if you're thinking about powering your application, you're looking for enterprise capabilities. You need to be able to mix and match data types. You need to be able to match or mix vector data with other data types, including time series, relational data, JSON data, so on and so forth, right? That's where the future is headed. So obviously, vector specific databases offer very little capability there. And one last thing I would also keep in mind is, as people are looking at making these decisions, think of the fact that, think about the broader enterprise capabilities, things like ACID compliance, HA capabilities, DR, point-in-time recovery, multi-AZ failover. These enterprise capabilities take a long time to mature. Like, we developed them over 12, 13 years, right? And a lot of these newer entrants or new databases really leave a lot to be desired when it comes to enterprise capabilities as well. So those are some of the key things you might want to keep in mind as you're looking about adding a vector specific database to your equation. So our suggestion would be to, instead of focusing on a vector database specifically, why not go for an enterprise grade database that has vector capabilities, right? So something like single store that gives you a broader stroke and a broader array of capabilities that goes along with your vector capabilities.
Awesome. Good stuff. With 1 minute left, I think we should move on from the questions and start to wrap up. Just quick note before we announce the AirPods winner. As I mentioned during the intro, next week we will be presenting how to drive 100x faster analytics for your MongoDB apps. During that time, Akmal, who you've seen here today in the panelist group, Akmal will be presenting how to drive 100x faster analytical queries on JSON using the MongoDB API that doesn't require any query changes or transformation. It's very cool. Feel free to register right now at the link that's on your screen. I'm also going to put that into the chat. You can use that QR code too if you like. There it is in the chat. The announcement you've been waiting for, today's AirPods winner goes to Fat Tran, software engineer at SailPoint in Toronto, Canada. You've been active in the chat as well. It's good to see you. Congrats. thanks again for joining. If that's not you, don't give up. We're going to announce one more AirPods winner by the end of the day for anyone who has tried out the GitHub demo. So feel free to keep an eye on your email. I'm going to send out the webinar recording for everyone along with this this GitHub link that I put in chat. I'll put that in chat one more time. So try that all out. Thank you so much for joining. Thank you to Jason for an awesome presentation today. And thank you to Akmal VJ for joining the webinar support team. Have a great day, everyone. We really appreciate your time.
Thanks,
Bye-bye.
everyone.
Bye, everyone.